Good morning, students. So we'll continue our discussion today on elasticity. Today we will look into one important concept in elastic behavior, which is principal stresses. So the reference from where you can read more about it are chapter 1 in the book by Hosford and chapter 2 in the book by Dieter. We started with normal stress and looked at planes where both normal and shear stresses were acting. So if you remember our earlier drawing, we were looking, so some weight was put over this and we were looking at stresses under normal condition. And then we also looked at a particular plane, which was like this. So we found that on these oblique planes, we have both normal stresses and shear stresses acting. We can also work backwards in the sense that we can start with a condition where both normal stresses and shear stresses are working and find a plane where no shear stresses are acting and only normal stresses are acting. So these kind of stresses are called principal stresses. We can find a plane where and these are what are termed as principal stresses. So the normal stresses under that condition are called. We will understand this with the help of some examples. But before that, what is the formal definition? So formal definition is that principal stresses are maximum minimum stresses and so if you look at a particular system, so for example, let's say we are looking at this system. So in this, if you look at various planes, there will be different amount of normal stresses and certain plane will have the maximum normal stress. So that value of normal stress would be called principal stresses. And in that particular plane, you will have no shear stresses and those planes would be called principal planes on planes, and the planes are called principal planes. It is this concept is very useful because it helps to simplify the overall thing. You can look at the element where only principal normal stresses are acting, and hence a lot of important parameters can be obtained. And also this principal stresses would also be useful, as you would see, when we are trying to find the onset of yielding. So usually the equation that you will obtain will involve all the 9 stresses, but then the same equation can also apply to the condition, to the element which is rotated in a way where only principal stresses are acting, and thus there are only 3 elements acting on it, and hence you can get a much simpler equation for finding the onset of yielding. how do we find the value of the principal stresses? So there is a equation. We will not derive that equation. We will look at that equation, and you would see that there are some parameters which are called invariants, and those invariants are related to the values of stress and strain. And these invariants, as the name suggests, their values would remain invariable no matter what particular orientation of the element you are selecting. So for finding the principal stress for any particular given element inside a given component, so you will know all the values of stresses, shear stresses and normal stresses, and from that you will calculate the invariants. And once you have the invariants, you will use this equation to calculate the principal stresses. So as you can see, this is the equation. So sigma p is the variable, which is the root of this equation, would give you the 3 principal stresses. As you can realize, there will be normal stresses along the 3 directions. So 3 roots would be found, and therefore we have a cubic equation. So roots of this equation gives principal stresses. And what are these invariants? So these invariants, as I've already mentioned, their values will remain invariable or constant no matter how you orient the element. So you have the one particular point inside the component where you want to calculate the stress with the state of stress. So for that particular point, you can have various orientation, and no matter how you change the orientation, these values I1, I2, and I3, they will remain constant. So I1 is given by sigma xx plus sigma yy plus sigma zz. I2 is equal to sigma xy square So these are the components for in I2, and for I3, we have so these are the values of the invariants. And as you can see, these values of invariants are described in terms of xx, yy, xy, meaning all the normal and shear stresses are concerned. But then, as we said, it is invariant. It means that these would be valid even if you are talking or taking the element in orientation where you have only normal stresses, meaning principal stresses. And therefore, in that condition, we will write, so the principal stresses we are defining or writing nomenclature is to use the subscript 1, 2, 3. So sigma 1 defines principal stress 1, I2 defines principal stress 2, I3 defines principal stress 3. And therefore, these values of I1, I2, I3 will translate to, so you can go back and look at over here, sigma xx, sigma yy, sigma zz, which would be basically, there will be sigma 1, 1, sigma 2, 2, and sigma 3, 3. So this becomes sigma 1, or sigma 1, 1 is same as sigma 1, sigma 2 plus sigma 3. I2, now here you can go back and see that there will be no, in the principal plane orientation, there will be no shear stresses. So these three would be 0. And what you will have is only this one and this one. and this one and this one and this one and this one. So this becomes 1, this becomes 2, 2 and 3 and 3 and 1, and therefore this becomes sigma 1, sigma 2, and similarly if you look at I3, if you get rid of all the shear stress component, then all these terms go away and you have only the first element, which means it will become sigma 1, sigma 2, sigma times sigma 3. Now let's try to calculate the values of sigma I1, I2, I3 for the two conditions for the example that we had discussed earlier. So let me draw that condition again that we had earlier. So here, given that the stress remains constant, so this whole thing can be taken as single point because the stress are not changing. If the stress were changing, then one point would be considered different from the other point. And with that respect, we can assume this is 1 point, or 1 point represents the whole element. So this is one condition. The other condition where we had the oblique plane. So the element can be assumed to be something like this in this case, and this becomes sigma x prime, and this should be sigma. Now this sigma y prime can be written as and sigma. So where this theta is the orientation. So as you can see, if theta were 0, then sigma y prime will be equal to sigma yy, which is what you would expect. And sigma x prime is normal to this. So when theta is equal to 0, this sigma x prime will become, this is sine square theta. So there is a square term because there is also the effect of area, and the other one is the direction of the force. So we are taking the component of the force as well as the component of the area, and therefore we have the square term. If you go back to the notes, you would see this is what the relation was coming out to. Now we have these two conditions. We will find the invariant in both the conditions, and as I said, as we have already we are expecting that since it is an invariant, therefore the values should remain same here and over here in the left and the right conditions. So for the left I1, we have sigma xx plus sigma yy plus sigma zz, and therefore the only element that we have here is sigma yy. For I2, if you go back and look at the values, all the values are 0, and therefore it turns out to be equal to 0. For I3, again, all the components for I3 turns out to be 0, and therefore I3 is equal to 0. So this is the value of I1, I2, I3 that we obtained for this left condition. Now we must get the same values for this oblique condition because it is representing the same element. Only the difference is in orientation, and as we have said, that invariants should remain unchanged when we change the orientation for the same point. Now coming to I1, so I1 is equal to sigma x prime plus sigma y prime, but and the third term would be sigma z prime, but that is 0. So sigma x prime and sigma y prime, they turn out to be sigma yy cos square theta plus sigma yy sin square theta, and therefore it is sigma yy. So this one is correct. So this part turns out to be correct. Now going to I2. So I2 is x prime y prime square plus sigma y prime z prime square plus sigma z prime x prime square minus sigma x prime sigma y prime minus sigma y prime sigma z prime minus sigma x prime. Now over here, this term is 0, this term is 0, this term is sorry, not this term. This term is 0 and this term is 0. So we have not defined the x prime y prime. Let me write down. This is something I missed earlier. So sigma x prime y prime is equal to sigma y cos theta sin theta. Again, this is something that we had done earlier. You can go back and look at the notes. Now when we come here, so we will have x prime y prime equal to y cos theta sin theta. So y square is cos square theta sin square theta minus sigma x prime minus sigma y prime. So this is sigma y square sin square theta. So again, this is also. So these two terms are equal, and therefore this turns out to be 0. And therefore I2 is also equal to 0, which is same as on the left hand side or the first condition. Now coming to I3. For the I3, you would see that these are the elements xx, yy, zz. So zz is 0. So this term goes to 0. All the other are anywhere 0. So I3 is also 0. So what do we see? That yes, indeed, invariants are same in both the cases. And this is not some, you can say, coincidence, but as you would see, this is the way it will be for all the conditions. Okay, so now moving on, we will look a little bit more about the principal stresses. And as I mentioned earlier, that when we are talking about the principal stresses, they are normal stresses when there are no shear stresses. And there will still be 3 in number for the 3 different planes. So we will have so this is usual nomenclature, sigma 1, sigma 2, sigma 3, and by convention, sigma 1 is greater than sigma 2 is greater than sigma 3. So sigma 1 is the algebraically the largest principal stress, meaning including the positive and negative sign, whichever comes out to be the highest number, that would be defined as sigma 1. So this is the order sigma 1, sigma 2, sigma 3, and sigma 3 would be the smallest one. So now let's look at some simple examples. So let's say you have a T MPa is the normal stress, and there are no shear stresses, and 50 MPa is the normal stress in this direction. So what will be the value of sigma 1, which is the sigma 1 value? So yes, this is the sigma 1 value. So sigma 1 is equal to 80. What is sigma 2? Sigma 2 is 50. And what about sigma 3? Is there any sigma 3? Yes, there is indeed, because this is the value here is 0. So the stress acting in this direction is 0. So that is the value of sigma 3 equal to 0. Now let's look at another example. So here 80 is still acting on the top face, but 50 is now acting in the compressive direction. So what is the value of sigma 1? So algebraically, still this is the highest value. Sigma 1 is equal to 80, and there is a unit of megapascal, which is there for all of these. Sigma 2. Now you may be tempted here to say that minus 50 is sigma 2, but that is not the case. Here also you have 0, and amongst minus 50 and 0, 0 is higher. So sigma 2 will be 0, and sigma 3 will be equal to minus 50. So that is how the sigma 1, sigma 2, and sigma 3 are defined. Now moving on, let's look at one example. So let's say you are given and here you are given that sigma x is equal to 10, and again I am assuming that the units are in MPa. Sigma y is equal to 8, sigma z is equal to minus 5, sigma yz is equal to sigma zy is equal to 5, and sigma zx equal to sigma xz is equal to minus 4, and sigma xy is equal to sigma yx is equal to minus 8. So you are given all of these. Now you have to find the values of I1, I2, and I3 for this. So again, we will apply here. Let me just write the title, applying to earlier example. I1 we know is equal to sigma x plus sigma y sigma z, and since we will be able to find I1, I2, I3, we should also see what will be the values of principal stresses that we can obtain from these given conditions. So here these are given. So this is 10 plus 8 minus 5 is equal to 13 MPa. Actually, I would not write the units because there will be some square terms. So there it will become megapascal square. We will assume that the units are consistent with each other. I2 is given as sigma xy square plus sigma yz square plus sigma zx square So putting in the values, this will become minus 8 square plus 5 square minus 4 square minus 10 into 8 minus 8 into minus 5 minus 5 into 10. And you would see this will come out to 115. So that is the value of I2. Now calculating the value of I3, which is sigma xx, sigma yy, sigma zz, plus 2 sigma xy plus 2 plus y sigma yz plus sigma zx minus sigma xx sigma y z square minus sigma yy So this, when you put in the values, this is 10 into 8 into -5 plus 2 into -4 into 5 into -8 minus 10 into 5 square -8 into -4 square plus -5 into -8 whole square. And when you solve it, you would see that this comes out to -138. Okay, so now we have the value of I1. I1 is 13, I2 is 115, I3 is -138. And therefore, we can put it in the equation form for finding the principal stresses. Sigma p cube minus 13, sigma p square minus 115. So this is I2. Sigma p plus 138 equal to 0. And this is a cubic equation which you can solve using any of the solvers, like mathematical. And what you would get is that sigma p is equal to 1.079. That is one value. Other value is 18.72, and still other value is 6.82. So again, we can see that these are three values of, as you would expect, because there are three principal stresses. So this one is sigma 1, this one is sigma 2, and this is sigma 3. So the concept of principal stresses should now be amply clear to you. We are, well, once we get the invariants from a given condition, we can find the principal stresses, meaning our orientation. So far, we have not tried to look at the angle theta, but this is not something we are trying to obtain yet. And you can easily obtain that theta, but we will look at it a little later. What we have found out so far are only the values of sigma 1, sigma 2, sigma 3, meaning let's say there was this orientation and then you rotated it in some other condition. So here, earlier one, you had normal as well as shear stresses acting, but now you have only normal stresses acting. So we have found the values of those sigma 1, sigma 2, sigma 3, but still not given you the equation for finding the theta. We'll come to that. So for that, before we are able to do that, let's again talk about transformation. We talked about transformation earlier, which was a very general equation. Now we will look at transformation for a specific case. So in engineering, you would see that the components or the stress conditions, loading conditions for a material are usually either plane stress or plane strain condition. And therefore, when we are talking about transformation, our task becomes much easier. So let's say we have a component which is like this. As you can see, it is a thin element, and therefore there will be no, and let's assume that there are no shear stresses on the Z side, Z component. So basically, there may be normal stress in the Z direction, but there are no principal stresses. So the conditions that you would usually see are when shear stress on one plane is 0. Normal stress. So this becomes the principal stress in that direction because there are no normal stresses. Sorry, no shear stresses. We are not talking about the other parallel directions along these, but along this particular direction. For this particular direction, we have only normal stress acting, and therefore this becomes the principal stress. So let's say this is Z direction. So normal stress in the Z direction is a principal stress. other two principal stresses lie in this plane. So this is a plane, this whole plane. So other two stresses lie in a so for this particular situation, which is very common we encounter in engineering, we can find a simple transformation rules. So to describe it in terms of element, what we have here is so here you may have shear stresses, here you may have shear stresses, but not over here. So there are no tau term over here. That is what we have usually, and in this particular case, if you want to transform, so if you look at one cross section, so you will have sigma y, sigma yx, sigma x, so this is plane stress condition, and most of the time when you will, because your third direction, you already have a principal stress, so the rotation that you would need is only in this plane, in the plane that is shown over here, and that kind of rotation is much simpler to describe. So plane stress transformation. So you are given something like this. It is your original x-axis, it is your original y-axis, and now you want to rotate and find stresses in another axis which has x prime and y prime, and this is rotated by an angle theta. So if this is theta, then so basically this is normal parallel to the y direction. In the original xy you had, this is also sigma y, and this has sigma xy, this as sigma x, and this has sigma xy. Now in the, and if the area that is on which this is acting, so let's say this area is delta A. So first let's look at sigma x prime y prime, and if we call this area as delta A, then the force acting here is sigma x prime y prime delta A. And similarly, if the stress acting here is sigma x prime, then the force acting here is sigma x prime delta A. On the other hand, here the stress that is acting is sigma x, and since this is delta A and this is theta, so therefore this one becomes the area into, to calculate the force, the area, this one is delta A cos theta, and therefore sigma x times delta A cos theta is the force acting in this direction. And similarly, sigma xy is the shear stress and area is delta A. cos theta. Here this is sigma xy, and area here is delta A sine theta. So this is a triangular element, and if it is not rotating, it remains stationary under equilibrium, then these forces must balance out. And it is on this principle that we will be able to find a general relation for a plane stress transformation. So let's look at the stresses along x-axis, along x prime axis actually. So the overall body is not moving, therefore sigma f x prime is equal to 0, and therefore we know that the total sum should come out to 0, and therefore we can write it as 0 equal to sigma x prime delta A, that is the force acting along the x prime direction, minus this is the force which is acting like this, and we will have to find a component along x prime. So this becomes sigma xy delta A cos theta times so this is sigma xy delta A cos theta, which is acting over here, and into sine theta term minus so this is the other term, which is sigma xy into delta A sine theta, and if we take a component, this becomes cos theta, and then there is this force, we'll again take a component, so this becomes minus cos theta, and there is also the sigma y term, which is here, again taking a component, and when you equate it, you would see that this sigma x prime would turn out to be sigma x equal to sigma x cos square theta plus sigma y sine square theta plus sigma xy 2 sine theta cos theta. So this is the equation that we obtain when we are balancing the forces along x prime direction. Now we can balance the forces along y prime direction, and again, since it is in equilibrium, we know that it should turn out to be equal to 0. So again, let's look at the components. So first, this is the y prime component, which is this one, and then we will have to take the components of each of these by taking either sine theta or cos theta. So sigma xy So these are the various components we have taken along the y-axis, and we know this will be 0. And when we simplify or take away all the 0 elements, then what we see is that sigma x prime y prime is equal to sigma y. And this is something that you should try on your own. and you would see that it is that to ensure that this is what it comes out to. And this will also give you a practice and to how to derive this. So what we have here are equation for sigma x prime and sigma x prime y prime. So this will give you rotation. So you have stresses, let's say in the xy coordinate, then this equation lets you get the normal stresses along x prime y prime direction, and also shear stresses along x prime y prime direction. So this is the plane stress transformation. Now this plane stress transformation can be made a little bit more, you can say, simpler or to look if we apply some of these trigonometric equations. Okay, so but before that, let me just highlight the two equations that we have here. And remember that we have obtained the equation for sigma x prime. Now sigma y prime will only be the same thing, but theta will be theta plus 90 degrees. Okay, so then you can get sigma y prime, and therefore sigma x prime and sigma y prime are not very different. Now, if we apply some of these trigonometric equations, which are the ones that I'm talking about. So these are the equations that I'm talking about. Cos square theta is equal to cos 2 theta plus 1 by 2. And similarly, sine square theta is equal to 1 minus cos 2 theta by 2. So basically what we are doing is transforming this equation gets transformed to from theta to 2 theta format. And there is a reason. You would see why 2 theta becomes a characteristic value compared to theta. And another equation that may be handy is 2 sine theta cos theta is equal to sine 2 theta. And similarly, cos square theta minus sine square theta is equal to cos 2 theta. So now once you apply these equations over there, what you would get are the following equations. So this will become your go-to equation whenever you want to do any transformation. Sigma x prime equal to sigma x plus sigma y by 2 sine 2 theta. And like I said, sigma x prime and sigma y prime are same thing, only that they are rotated by 90 degrees, as will also be obvious from this. So the first term does not have any theta, so it remains same, sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta. So as you can see, when theta is rotated by 90 degrees to theta, it becomes 180 degrees. So it is still cos 2 theta, but there is a minus sign. And over here, we will have again again minus sign. So this gives us sigma y prime and sigma x prime. Y prime is equal to right 2. So this is an equation that will become very important for you whenever we are talking about transformation, any kind of transformation. So this is given in the original frame, sigma x, sigma y, and sigma xy. And now you can get sigma x prime, which is oriented at an angle theta, and sigma y prime, which is at 90 degrees to sigma x prime, and sigma x prime y prime, which is the shear stress for the xy orientation. And these equations will come in very handy. Now, once you have this equation, one important question that may arise to you is how to obtain principal stress from this, because we have these stresses. So shouldn't there be any way where we can get principal stresses from this? And the answer is yes. Why? Because we know that principal stresses are where the stress value is highest. That is one characteristic. The other characteristics is that on that particular plane there are no shear stresses. So going with the first condition, we know that d sigma x prime by d theta is equal to 0. So if we differentiate the first equation with respect to theta, we should, and assuming that it is giving us the maxima, or we can check for that, d2 sigma x by d theta square is less than 0, then we would know that if it is less than 0, then we know we are getting maxima. So let's differentiate this, and what you would get is 0 equal to 0, and cos 2 theta, when you differentiate, it becomes sigma x minus sigma y by 2. Cos 2 theta becomes 2 sin 2 theta. And the second term, which is sigma xy sin 2 theta, that becomes 2 sigma xy cos 2 theta. Or in other words, we have tan 2 theta equal to so what is it that we are getting from this equation? This is the equation that I mentioned earlier, would give you the orientation for the principal stresses. So this 2 theta, tan 2 theta, if you get 2 theta equal to tan inverse of this, will give you the theta at which you would get maximum normal stress, and the shear stresses would be 0. On the other hand, we can also, from this also you can get the orientation where you can get the maximum shear stress. But let's do it independently, and for that we know that the maximum shear stress, the plane where you will have only the shear stress, the plane where you will have the maximum shear stress, then for that you will have d sigma xy by d theta equal to 0. And again, when you differentiate, what we get is the equation like this. And in this case, the theta where the shear stress would be maximum, what you would get so this is the relation for the condition where you will get maximum shear stress. Now, what do we see the orientation for? So this is the shear orientation for maximum normal stress. And this is giving you the orientation for From these two relations, you can clearly see that the orientation for maximum normal stress and orientation for maximum shear stress would be away by 90 degrees. Okay, so these are some of the important things that we can notice from here. Apart from that, a few more things that we can notice, and those are like sigma x prime plus sigma y prime is equal to sigma x plus sigma y. So that is the sum of the normal stresses on two perpendicular planes is an invariant quantity, and that we already know because sigma z is a constant and it is independent of orientation or angle. So for that particular plane orientation. And another one is something we have already discussed: maximum normal stress and maximum shear stress orientation are away by theta equal to 90 degrees. And maximum stress occurs at an angle halfway between maximum and minimum normal stress. Halfway between max and min normal stresses. Okay, so there is one thing that I made a mistake here. So maximum normal stress and maximum shear stress are away by 2 theta equal to 90, not theta equal to 90 degrees, because we have measured these in or counted these in terms of 2 theta, which would mean that theta, but that they are away by theta equal to 45 degrees. So in general, that would mean that if you have some cubic structure like this, and you are applying only normal stress here, then at this particular orientation, you will have only shear stress and no normal stress. So this is 45 degrees away. And when you go back from here to here, you will have the maximum normal stress. At this angle, you have maximum shear stress. And if you come here, you can see this is 0 normal stress. So between maximum and minimum normal stress, you see that there is a maximum shear stress condition. So the points that have been mentioned can be understood with respect to this particular drawing. The variation of normal stresses and shear stresses occur in the form of sine wave with a period of theta equal to 180 degrees. So if you were to plot normal stress versus theta and shear stress versus theta, you would see that it is a sinusoidal function with a period of theta equal to 180 degrees. So after 180 degrees, again, it will come back to its original position and follow the same path. So these relationships that we have described here are true only for 2D state of stress. Okay, so we have today talked about one important concept about stresses, which is principal stresses, and we also looked at plane stress transformation. And before we go, I would like to show you important figure. So here what you are looking at is a small pillar, which is also called as micro pillar, that you are able to make in FIB, focused ion beam electron microscope. So this is of the order of, you can see the scale is given here, 2 micrometer. So the diameter is something of the order of 5 micrometer, and the length may be of the order of 20 or 40 micrometer at the most. And what we do usually, why researchers make this kind of pillar, is to characterize properties, particularly mechanical properties of one particular single crystal of a material, and that too in a particular orientation. So this would be a single crystal, and then one can compress it. So you can see that after compression, what they are getting, since it is a single crystal, they are getting shearing. So they are all parallel shears. So the shearing has actually taken place just as we would imagine. So on one certain particular plane, the shear stresses are very high, and therefore the material collapses along those planes. Now the question for you to think for the time being is, what are these angles at? How are they oriented with respect to the normal direction? How can we find out at what particular orientation they would fail? Okay, so with that, we will close today's session with this thought for you to work upon, and we'll come back. And next time, what we will be looking at is again another important aspect, which is Morse circle. And you would see whatever we have learned today, you would be able to imagine and represent in a much better way using the concept of Morse circle. So thank you.